Here we are in section 5.2, which is properties of rational functions. And we've got several problems, but nothing to the extent like section 5.1 was. I will guarantee there will not be 6 videos for this section. We begin 1, 2, and 3. We need to find the domain of the rational function and realize rational functions are functions that have basically fractions within them. And so that's what we're looking at. And we need to remember that whenever we have a fraction, the denominator can never equal 0. And so that's what we're really interested in. So if we look at number 1, we have r of x equals x plus 6 over x squared minus 9. Well, what that simply means is x squared minus 9 cannot equal 0. But what we're going to do is we're going to find where it does equal 0, and that tells us what values we have to exclude, and then we'll exclude them once we list our domain. So it's very simple. Add 9. X squared equals 9. Take the square root of both sides so that x will equal either positive or negative 3. So these are the places where it can't exist, at positive 3 and negative 3. So the domain will be everywhere else. So it goes from negative infinity all the way up until negative 3. Then it goes from negative 3 until 3. And then it picks back up at 3 and goes forever. And so that would be the answer for number 1. Number 2, once again, what we look at is the denominator, x cubed minus 125. This cannot equal 0, but to find out what we're going to exclude, we will set it equal to 0 and solve. Well, add 125 to both sides, and then take the cube root of both sides, and x is equal to 5. Now notice, since this is an odd exponent, it's not both positive and negative. Just keep that in mind. Now the domain would then be everything but 5. So how we show that? Negative infinity up until 5, along with 5 and beyond. And example number 3. Same thing, just a little bit more involved because we have 5x squared minus 4x minus 9 is the denominator. And so that cannot equal 0, but what we're going to do is we're going to set it equal to 0. And so I realize that this can factor to 5x minus 9 times x plus 1. And so set each one of these equal to 0. 5x minus 9 equals 0. So 5x would equal 9, or x would equal 9/5. Likewise, x plus 1, setting it equal to 0, x is negative 1. So these are the two values that it cannot be. So how do we show that in our domain? Well, we go all the way from infinity up until negative 1. Negative 1 has to come first because it's the least between these two. Then it starts back up at negative 1, goes to 9/5. And then it picks back up at 9/5 and goes until infinity. And that is the answer to number 3. Number 4 asks us simply to look at the graph and determine what's the domain in the range. This we have been doing for quite some time. So I look, domain, that's the x values. Are there any x values that appear like you'll never meet? Well, no, it's going to keep on going forever. But notice that dashed line there. That's called an asymptote. It will never reach that particular line, but it will keep on getting closer and closer. So let's see, the domain. It certainly will go all the way to negative infinity. But then I look, as it gets close to 0, my graph just goes straight up, in essence. And then when it picks up on the other side of 0, it's still going straight up, but it starts way down in the negative infinity again. But it certainly appears like it will go to positive infinity. But I look and see, well, there's one value that is very much missing, and that is the value of 0. Nowhere does x equal 0. And so my domain would be all the way up until 0, and then it picks back up at 0 and goes on forever from then on. Now the range, on the other hand, is what are the y values? Well, the y values, it goes just on the left part there, it goes negative infinity all the way to positive infinity, and there's nothing that it's going to block out as far as a y value is concerned. So the range is negative infinity all the way up until infinity. Now I mentioned the dashed line on the graph, and that's how I want to show, and that's how I want you to show in your graphs asymptotes. If there's an asymptote, a boundary that the graph will not meet at the extremes. It will never go over that line. It'll keep on getting closer and closer, but never quite there. And there's three basic types of asymptotes. There's vertical asymptotes, which are really the easiest to determine. There are horizontal asymptotes, which require a little bit more work. And then there are oblique asymptotes, or sideways, or crooked, however you want to call them. Officially they're called oblique, but they're the ones that are sideways or slanted. And so we're going to be looking at those. But we begin with the easy ones, the verticals, then we'll eventually get to horizontals, and then we will basically end on the obliques. So I look at this and I'm asked, use the graph to find any vertical asymptotes. Well, okay. Even though it's not shown as a dash, I see the graph keeps on approaching x equals 0, or in other words the y-axis, but it never seems to cross it. So I would probably have to assume that's the vertical asymptote there. And so my vertical asymptote for number 5 is x equals 0. Now realize asymptotes are equations of lines. So if you just put 0, that will be guaranteed wrong. It has to be x equals 0 because that is what the equation of the y-axis is. By the way, the equation of the x-axis is y equals 0. But continuing on. Number 6 asks us to graph the function using transformations. And here is where we need to go back a little ways. We need to think of, first of all, what's the parent function? The parent function is the reciprocal function 1 over x, because that we've got something over x something. And so we have to understand a few things. First of all, that negative says reflect over the x-axis. The 2 says stretch by 2. And the minus 3, well, it is directly connected to the x, because remember that the fraction bar is a connector, or a grouping symbol. And so that means it doesn't behave, so it's going to go 3 to the right. Now, if we go back to the parent function, it's 1, 1, 1/2, 2, 2, 1/2, and it looks like this. And we already have dealt with asymptotes. We had an asymptote of y equals 0 right along here. It gets closer and closer to that value, but never crosses. And it gets closer and closer to this, but never crosses. So we've already dealt with asymptotes, we just haven't really dealt with them in detail. Now realize anytime you do a transformation like right, left, up, or down, that will also change your asymptotes. So if I'm going to go 3 right, I have an asymptote right here. So that means it's going to go 3 to the right. The new asymptote is going to come out here. So I'm going to draw my new asymptote. I've dealt with the asymptote, and basically, since there's no up or down, my new set of axes is going to be here and here. The x-axis hasn't changed. It's only the asymptote here becomes my new y-axis. And so then I also need to reflect it. So instead of going like this and like this, it's going to go like this and like this. So I know that much. And then finally I'm going to stretch it by 2. So instead of 1 over and 1 down, it's going to be 1 over and 2 down. Or 1 this way and 2 up. and then the 1/2 will go to 4 and to 4 because we're stretching it by 2. And instead of here when it would normally be 1/2, we're going to go to the full value of 1 and the full value of 1. And then we're going to be able to draw our new graph that looks like something like that. So it's not this one here and this one. Let me go ahead and erase those so get rid of as much confusion as possible. This is the actual graph that we wanted, but we just had to look at several things. The reflection over the x-axis makes it look upside down or backwards. The stretch by 2 just makes it seem a little bit longer. We will continue with the second video for section 5.2.